coding, and so all you need to do is so it's given for a constant angle theta, so which means d theta should be 0 because theta is a constant, right? And it's straightforward. And the next one is so which means you can basically reduce this line element dl squared into one component, right? Because now for a 2D for a three-dimensional spherical coordinates, you normally have three components, that is dr, d theta, and d phi. And since the theta is a constant, d theta will be 0, and also when r is constant, dr is 0, right? So which means you only have one element in the metric, so which means the equation will be dl squared equal to r squared sine squared theta d phi squared. And this equation for 3D we have talked it before in the note, right? So I'm directly using it. So which means now you have the line element, and so which means dl will be r sine theta d phi. And so what you need to know here is to find the circumference. You can use the geometry, and you know that this length is the radius of the sphere, so which means the radius of the circle will be r sine theta. And if you get a small angle around the circle, that will be r sine theta d phi. So that's what you can see inside this integration. And then when you need to find the circumference, you have to integrate it around the circle, right? So that means you have to go for phi coordinates starting from 0 up to 2 phi to complete the circle. So I guess all of you can understand it, and the answer will be 2 phi r sine theta, right? So it's just a simple example. And however, there is something that you have to take from this example, that is, if you look at this, the last answer for the circumference, the usual answer you normally get in a Euclidean space is just 2 phi r, right? So that's the circumference of a circle. But here the answer that you get is 2 phi r sine theta, and this is actually a result of working on the curved surface of a sphere, right? So that's why you get this bit different result right here. And so I assume that all of you can understand it, right? And right, so let me see it. Now start from here. So let me, anybody have any questions here? Right, so one thing, make sure that once these questions are submitted, you work out it yourself and submit it, right? Because the way that I do this part is a bit different than just having the lecture. So what I'm doing is just introduce you the different, different mathematical equations, and after that I want you to go through the note and work out yourself these examples, right? And also make sure once again that you write this note yourself and keep it with you, because these are like, mathematical equations that you have to write yourself and understand it, and look at it and see how these things are written, right? Especially when we go into the next section about tensors, this is specifically very important that you write tensors from a pen and paper, on the paper yourself, right? Because there are, different indices that you need to keep track on. And so this is why I will, rather than just taking the whole time to doing the lecture, so at the end I will, leave some work for you so that you can work out yourself, right? Because this section works in that way. Right? So let me, right now for the today's lecture, so let me start the next section. And most of the time I used to upload the note ahead of time, and this note is also uploaded. Just give me a minute to share this new screen. Slides. Right, so I assume that all of you can see the new set of slides that I am sharing, right? Now the today's topic is scalars, contravariant vectors, covariant vectors, and tensors, right? That's a different section now. Having this idea about the metric and how to write the line element, and also the Einstein's summation convention, which we have learned from the last section. Now we are going to talk about this section about scalars. Of course, you know what is a scalar, right? And also a vector, which we called as contravariant vector. And then there is a new word called covariant vectors. And then we will move on to tensors, right? So that will be the topic for today. And at the same time, probably at the middle of the lecture, maybe towards the end, as usual, I will again share one video with you, just to give you an idea about what we are talking, and about some of these key concepts about general relativity. Right. So I am now sharing my note. So if you cannot see it, then please let me know, right? And as an introduction to this section, now this section specifically, there is a branch in mathematics which is especially concerned with this manifold. So we introduced what is a manifold in the last section, manifolds and the objects that move in these manifolds, right? So this is why we introduced the manifolds in very first set of lectures. And this branch of mathematics that works with these manifolds and objects that move on this manifold called as differential geometry, right? So the students who have followed mathematics may know about this section about the differential geometry. It's a separate section that you have in mathematics, which is pretty much related to these tensors and these concepts that Einstein has introduced. But for our purposes, we will briefly learn each of these things because that will facilitate us to understand this Einstein's, especially the mathematical background behind Einstein's field equations. Right. Now, as I told you, we talk about two types of vectors here. The first one is called contravariant vector. Now, these vectors are normally, this is an object with one upper index, right? So what that means is, so let me show it. When you have contravariant four vectors, as you saw in special theory of relativity, you have, four components, right? We normally represent these contravariant vectors by an arrow over a letter. And if you use the Einstein's summation convention, let's say you have few components, then you can write it in this way, right? So you have the vector right here, and then you write V upper alpha and the lower alpha, which means these two components, V alpha, E alpha, are actually components. One is the component of the vector, and E alpha is the basis vector, right? So the basis vector means, just think about this simple Cartesian coordinate system, which you have, if you write something in Cartesian coordinate system, let's say you write a distance R, you use to write xi hat plus yj hat plus ck hat, right? Then this x, y, and c are the vector, the components, and the basis vectors are these I, j, and k vectors, the unit vectors, right? So those are the basis vectors because we write the vector in terms of those basis vectors, right? So those are called basis vectors. Now here, since we are going to work in this curved space, in general, we define these basis vectors as E alpha, right? Now, as you see that even in the Cartesian coordinate system, you have to write it in 3 times, xi hat plus yj hat plus zk hat, right? To avoid this complex writing, we use Einstein's summation convention, right? So this is what we learned from the last set of lectures. That means you write V alpha, E alpha, and as if you remember that I told you that if you have the same index repeated, you are going to sum over this particular expression using alpha, right? So that means, for example, if alpha goes to 1, 2, and up to 3, then you write V1, E1 plus V2, E2 plus V3, E3, like that, right? So this expression represents that complete, equation or the expression. Now these are called like contravariant vectors, which I guess you already know. And then there is a second type called covariant vectors. And I think some of the books also call this type of objects as one forms, right? It's the same name that you use. I mean, 2 different names that you use for the same thing. But as far as I know, this one form has a more deeper meaning. But covariant vector is, a word that normally we frequently used in most of the places that I have seen. But you may see instead of telling covariant and contravariant vectors, sometimes some authors use this word contravariant vector and one forms. One forms means covariant vectors. Right? It's basically the same thing. Now, these covariant vectors represent by a small tilde mark over the letter, as you see here. And in Einstein's summation index, you write the same thing as V alpha, E alpha, but just see the difference here, right? So that is the important thing. Now, when you have a contravariant vector, you have V alpha as the upper index and then alpha as the lower index, right? But here, what you have is, for the covariant vector, alpha is the component V alpha. Alpha is the lower index, and this basis vector has the upper index right here, E alpha, right? So these are two different things. So just make sure that you understand. This is V alpha, E alpha, V upper alpha, and E lower alpha for the contravariant vector. But for the covariant vector, you have E lower alpha and E upper alpha, right? So that's how it works. Now, sometimes so it is easy to remember this using this word. Basically, the covariant means, the co means that you have the index in the lower position, right? In the vector, sorry, in the vector component, right? V alpha, right? That's how you can identify or remember it, right? I mean, there is no relation between co and low, but I mean, you can remember it in that way, right? The covariant means, the co means that you may have the component, you have the lower index in the vector component, while in the basis vector, you have it in the upper index, right? Now, that's why I have mentioned here for the basis vectors, E alpha themselves are vectors even though they have a lower index. And the basis covariant vectors, which is E upper index alpha, actually covariant vectors even though they have upper indices, right? The reason that I have made this statement, if you go into the previous section, you can see that for the contravariant vector, you normally have this upper index. However, for the basis vector, you write it as a lower index, right? So that's why I tell you, even you have here as for the contravariant vectors, for the basis vector, you write it as a lower one, right? With the lower index, right? And for the covariant basis vectors, you write it as an upper index, E alpha. Right? But for the main component, you use lower alpha. Right? So this is, I mean, it's kind of, switch the position for basis vectors, for the covariant vectors and contravariant vectors, right? So make sure that you go through this carefully, because if you haven't done about anything about tensors before, this may be the first time that you are looking at these conventions, right? So it is very important that you go through it and understand, and there are places that you have to remember. So make sure that you go through this again and again, right? Now, I mean, this is actually a convention that's how we write covariant vectors and contravariant vectors, right? Now, there is an advantage of using this convention. The number one is this will make a very nicely balanced tensor equations, right? For example, when you write vector V, you can write V alpha, E alpha with one upper and one lower index, which will be useful, and you will see why it is useful in future, right? And the second thing is this depicts the basis vectors that transform like covariant vector components, and basis covariant vectors transform like vector components. Right? So I guess you probably would understand it. Now, if you look at basis vector, so that means a contravariant vector. A basis contravariant vector transforms like a covariant vector component, right? And basis covariant vector transform like a normal vector component or a contravariant vector, right? So just to make understand for you, when I say just the normal basis vector, so that actually means a contravariant vector, right? These are like normal vectors that you have. It is the covariant vector form that should be new for you. Right, now let's look at scalars. And all of you know about scalars. Scalars do not change during coordinate transformations, right? Now those covariant and contravariant vectors, you have these two forms because they are important in coordinate transformations. But if you consider scalars, scalars actually do not change during any coordinate transformations. And if you take temperature as an example, if you try to measure the temperature of a particular location, it would not change whether we explain it in Cartesian coordinate system or spherical coordinate system, right? So it will be the same temperature, right? So it doesn't matter what kind of coordinate system that you are using to explain the temperature, because temperature is a scalar which does not depend on coordinate system. If you have a particular temperature at a particular location, doesn't matter which coordinate system that you are using. So I guess all of you know about it. And then let's look at the contravariant vectors and covariant vectors. Now, one thing that we have to know is the relationship between basis vector and basis covariant vectors, right? Now, basis vector means this normal vectors, and then the basic covariant vector is the one, the type that we learned today. And if you write or take the product of a normal vector and a covariant vector, normal vector means a contravariant vector, and the covariant vector, the result can be written in this way, delta alpha beta, right? So what this means is product of these two will have a value of 1 if alpha equal to beta, right? Unless the answer will be 0, right? I guess I have introduced this delta notation last week to you. And the idea is when this contravariant vector, when they act on each other, basis vectors and basis covariant vectors, they disappear, which means you have to have the same type. And you can use this type of, information when you have a product of, when you apply a covariant vector into a contravariant vector like this. Let's say you have the covariant vector as P alpha, E alpha, and your contravariant vector is V beta and E beta. And when you multiply those two, then what you have is you write the components separately, P alpha, V beta, and then you have the basis vectors E alpha and E beta right here at the end. And these two, E alpha and E beta, you can replace from this expression right here, delta alpha beta. So that's what I have done here in terms of writing E alpha, E beta. So I have here delta alpha beta, which is a replacement for this product of two basis vectors, right? I mean, basis vector and a basis covariant vector. And what has happened here is this expression right here will only have a value only if alpha equal to beta, right? So that's the idea of a delta function, right? So it will have only a value which is equal to 1 when alpha equal to beta. Other than that, the value will be 0, right? So that means the answer will be P alpha, P alpha. So that means you take the condition alpha equal to beta, then you can replace all the betas from alpha, and then this delta alpha alpha will be 1. And your answer will be P alpha V alpha, and you don't need to worry about all the other terms, because when alpha does not equal to beta, the value of delta function will be 0, which lead to this whole expression will be 0 then, right? Then what you will have is this expression P alpha V alpha, right? Now, from the Einstein summation convention, if you have, let's say, 4 components, then alpha will run from 1 to 0 to 3, right? Or 1 to 4. And if that is the case, the product of this covariant vector and contravariant vector can be written as P naught V naught plus P1 V1 plus P2 V2 plus P3 V3, right? So that's how you write it. Right, so let's look at, I guess there is a picture which I cannot see it here. So let's now look at how you can transform between coordinates, I mean different types of coordinate systems. And here is a picture that shows you some information that how you can write an infinitesimal displacement, and keep this in mind. Let's look at that you can define a basis vector EW which is tangent to U equal constant. So what that means is, to look at this particular image, this is the basis vector EW, which is, tangent to this line U equal a particular constant. Now I have drawn it here specifically for U equal 2, but any constant would work, right? For any constant, you can write a tangent vector as EW. Right? So that's what you see. A basis vector EW is defined as a tangent to the U equal constant. And the same thing, another basis vector EU is defined as a tangent to the W equal constant, right? So those two are again here is the U equal constant, where you have this basis vector EW, and then here is the W equal constant line in this direction, where you have this basis vector EU, right? So they are tangent to a W equal constant and also U equal constant, right? And here is on the right hand side, you would see an enlarged version of the same thing. And since you have the notes, I hope that all of you have this picture with you, right? Right. Now you can write the component dx using those two basis vectors and infinitesimal displacement as du eu plus dw ew, right? So once again, if I go into this image right here in the right hand side, so this is dx vector that you can write it in terms of du eu. This is an infinitesimal displacement multiplied by the basis vector into that direction, right? That is EU, as you see here, plus this vector right here, dw ew. So that means infinitesimal displacement dw multiplied by the relevant basis vector, right? So this dx will be this expression plus this one right here. So that's what I have here. Dx vector will be equal to du eu plus dw ew, right? Right. Now the same thing, if you need, you can write using Einstein's summation convention again as dx iei. So what that means is again you have the repeating indices, that is in this I. So which means you can write this as a summation. If you have two components like this, you can write this dx1 e1 plus dx2 e2, right? That means dx1 will be basically x1 will be equal to u, right? So that will be du eu plus, and the dx2 will be x2 will be again equal to w plus dw ew, right? So you can write it in this way, and in brief, you can write the expression in as dx equal dxi ei instead of writing this long expression, right? Using the Einstein's summation convention, right? Now, in the similar way, if you using these new coordinate basis vectors, you can define a contravariant vector v, is a normal vector, at the point P with components Vu and Vw, right? In the similar way, you can write a contravariant vector in that way. So this is a small displacement, but if you think about a different vector, you can write the same in this form. That is, if you have two vectors Vu and Vw in the two different directions, you can write V as Vu Eu plus Vw Ew, or you can write it directly Vi Ei, right? Now, what I want, based on what you have there, what I want to introduce here is how you do this contravariant coordinate transformation, right? So let's assume that in a 2D space, if you want to express an infinitesimal displacement dx in terms of another set of coordinates p and q, right? So let's assume that you have this infinitesimal displacement dx that we have introduced in the previous slide, and you have to you need to express it in terms of another set of coordinates, right? So let me take those new coordinates as p and q, right? So yeah, both these p and q coordinates are functions of previous coordinates u and w. So there is a connection, right, between u and w and p and q. If that is the case, you can write a differential, and that is dp as dava p over dava u du plus dava p. I guess you know about these equations, right? This is how you can write dp and dq if both p and q are functions of u and w, right? Now, if you denote these new coordinates p and q by a prime and all coordinates by an unprimed notation, you can use the summation convention again to write this set of equations from one single expression, right? So this is what you have to understand here. So you have one expression right here, the second expression right here, completely different one, and for the first expression you have two expressions summed together, and the second one also you have two expressions summed together, and this whole thing right here you can write from one single expression like this using Einstein's summation convention, right? Now this expression tells you dx dash j equal dava x dash j over dava xi dxi, right? Now the number one that you have to understand here is, if you have the same in this index, then that should be summed over, right? So that means this I right here is here and I is right here. Now in this expression, you have the same index I repeated, which means dx, and this is the index that should be summed over, and the other index right here dx dash d and dava x dash d. So that you only have one index there in one side, so which means that index j should not be summed over, right? So that's how you understand it, but index I has to be summed over, which means if you need to understand these two expressions based on this particular expression that I have written here, the first thing is just don't think about this expression, just think about the other one. So you have dp double p over w du plus double p over double w dw, right? So that means let's say j equal just 1, right? And if that j equal 1, so this expression can be written as dx dash 1 equal dou by x dash 1 over dou by x 1 dx1 plus dou by x dash 1 equal over dou by x2 dx2, right? So then you have this expression can be written as a summation plus something, right? So that's what you see here, right? If you replace this x dash j by p, it will be right here, and then you have dou p right here, and then you summed over for u and w, right? So those are the two summed, let's say, indices, right? So that's how you understand it. Now, so why you have this j component right here is that is for the second equation, right? So for j equal 1, then you have this d p equation, and then for the second one, let's say j equal 2, what that means is this second equation dq, right? So that will be again equal to dou q over w du plus dou q over w dw. In that way, you can use the summation to express one equation, and these other indices will go to represent a separate equation. Like that, you can see that this is a nice way of summarizing a set of equations, right, which includes everything. So this is why this particular expression is very powerful, especially in a field like general relativity, right? So you can summarize everything into one single expression, right? But at the same time, you have to understand what that means, right? Now, if you go into the four-dimensional space, then what you have is you have in four-dimensional space-time, the components of contravariant vector must transform in the same way as the components of dx, right? Now, hence we can write in this way, right? So that means if you consider four-dimensional space, you have four components, so they should transform in this way, right? So that is the idea with two different coordinate systems. So you have v dash alpha equal dou by x dash alpha over dou by x beta times v beta. So that means basically you have four components added together, right here. So these are the components of coordinate transformation equations of a contravariant vector, right? So this is how coordinates transform in a contravariant vector. And once again, what you need to understand here is it is the beta component that should be changed. For example, if you have four components, like in four-dimensional space-time, so those four components will transform in this way, right? Each component will transform in this way. Now, so yes, if you take if you explain this in words, the v beta are the components of the contravariant vector v in original coordinate system x beta, right? So what I'm doing here is you have different terms, so I'm explaining each term here. V beta, which is this expression right here, v beta. So it is the components of a contravariant vector in original coordinate system, whatever the original coordinate system. Now here the original coordinate system is x beta coordinate system, right? And v dash alpha are the components of the contravariant vector V in the new coordinate system X dash alpha. Now you can see that if you go back to this particular expression right here, the alpha represent the new coordinate system, beta is the older coordinate system, right? So which means, so that's how these two are explained. And then this expression right here, da by x dash alpha over da by x beta term explains how old and new coordinate systems transform between each other, right? And this term represented by a 4x4 transformation matrix where beta would go from 0 to 3, as this is a 4-dimensional space-time, and this is how it looks like, right? Now you can see that the information that contains inside this small expression, right? So normally you would see only this expression, but that what that means is that you have all this information right here. So that particular expression da by x dash alpha over da by x beta actually has 16 terms there in the matrix, right? So you have to consider each one by one, and that is the powerful of this Einstein summation convention, right? Right. So I have a problem here for you. In flat space of the special relativity, assuming that an inertial frame S dash is moving with velocity v in x direction relative to another frame S, and I assuming that you probably have already done about these things in special theory of relativity, the contravariant vector v beta in the frame S has components 5, 0, 0, 2, and find its components in S. Basically, you need to do a small coordinate transformation, right? So I have given some additional information here. For the Minkowski space, the coordinate transformations are defined as, these are usual, equations that you probably have learned in special theory of relativity. Because Minkowski space is a flat space which have these coordinate transformations. So use that and use this information. And you have to find the components in S dash, right? So what are the components? Now you have the components in the frame S. You have to convert this into the as components in the S dash frame, right? So I will leave this, and also the gamma will be equal to 1 over square root of 1 minus V over C squared. And I guess all of you know about this information, and I just want you to do this coordinate transformation. And this will be your next problem, that I am not going to do it. And I assume that you already have done these kind of problems in special theory of relativity, right? So the idea here is just to make sure that you understand what you have done, right, in terms of coordinate transformation. So try this problem, and we will discuss about this next day. Right, so that is about contravariant coordinate transformations. Let's look at the covariant coordinate transformations. Now, this type of transformation works in opposite manner compared to the contravariant transformation, right? And if you consider this as an equation, this is how you write it. And V beta are the components of the covariant vector V curl in original coordinate system X beta. And then the V dash alpha is the components of the same covariant vector in the new coordinate system, right? And it is important to note that the prime coordinates are in the denominator, unlike the contravariant vector transformation equations. Now this is actually important here. The prime is now right here. But if you look at the previous one, the prime coordinate is right here, right? Make sure that there is a difference between these two transformations. Right. So it's the same components of the covariant vector, and so this is what I have mentioned. And the term da by x dash alpha over da by x beta term explains how old and new coordinate systems transform between each other. And this term represents a 4x4 transformation matrix beta that will go from 0 to 3, right? So this is, so basically what I have introduced here is what is a contravariant vector and what is a covariant vector, and how they transform between different coordinate systems, right? This is, basically there are a lot of mathematics here that involves, which means that you have to do it yourself, and because of that, make sure that you complete that problem and see whether you can understand these coordinate transformations. And next thing is, so we basically talk about scalars, contravariant vectors, and covariant vectors. Now let's look at the tensors, right, as the next section. Now, before we, if you look at these different mathematical laws in physics, they must be same regardless of the coordinate system we are using, right? And I hope that all of you know about this, because I mean, if the laws starts to change from one coordinate system to the other, then I mean, it will not work, right? Because these laws are, they explain different physical situations. And because of that, it is a fundamental, law in physics, that all these mathematical laws in physics that we use should be same regardless of coordinate systems we are using, right? So it shouldn't be depend on coordinate systems. Whether you use spherical coordinate system or Cartesian coordinate system or any other different coordinate systems, it doesn't matter. You should always, I mean, the mathematical laws always should be the same. And there is a specific name for that. This is called as the principle of general covariance, right? Now, the reason that the tensors are important here, because this transformation properties of tensor components are basis independent. So they don't depend on basis. If a tensor equation is true in one coordinate system, it will be true in other coordinate systems as well. Now, this is why tensor equations and tensors are important. Now, if we go into the general relativity, in general relativity, there are no preferred coordinate systems, right? And we use tensor equations to formulate the theory. And if you remember, when we did classical mechanics, I remember that I told you that it is important to select the correct coordinate system as well, right? I mean, it doesn't matter which coordinate system that you choose, still you will get the answer, right? But depend on the geometry of the problem, some coordinate system seems to be easier to work with, right? But for the general relativity, there are no preferred coordinate systems. We use tensor equations to formulate this theory of general relativity, and you will see how we work with tensors in coming lectures. Now, the next question that you probably will have is, what are these tensors? Because I have not introduced or defined this term tensor, right? Now, in one way, all the scalars, vectors, and covariant vectors that we talked up to now, are actually simple type of tensors. Other than that, we will use this tensor called Riemann curvature tensor, which is we usually tell that this is a 4-index monster tensor, which means this is a rank 4 tensor, which has a large number of components. And this tensor is used to explain the curvature of any space, right? Now, if you remember that using some of these videos, I have explained that these by the way, I will get some bit more time today, right? Since we couldn't do the lecture on Friday as well, not that much, but I will probably go into another 15 to 20 minutes to finish this section, right? And this Riemann curvature tensor is a 4-index tensor which explains the curvature of any space, which is important in general relativity, right? Because we always talk about the curvature of space-time here. Now, in general relativity, we will have to talk about the Riemann curvature tensor, and then we will introduce a new tensor called Ricci tensor, and then we will have another tensor called energy momentum tensor. And then combining some of these tensors, we can actually define another new tensor called Einstein tensor. And all of these type of tensors will lead to this final aim, which is about understanding or getting familiar with Einstein's field equations. Right? Now, because of that, you can see that why we need to look at tensors, because we are learning general relativity, which means we are going to talk about Einstein field equations. It has to be derived, not derived, actually you need to understand. If you need to understand it, you need to have the knowledge about the Riemann curvature tensor, Ricci tensor, and energy momentum tensor, and also about the Einstein's tensor, which will lead to these field equations, right? Now, this is why we have to learn a bit about these tensors and how to manipulate these tensors and all these things. Right. Now let's look at what is a tensor. Right. Now we can actually look at tensors in different ways, but I have mentioned here in two things. A tensor can be introduced as a mathematical object that represent by a collection of components that transform in a certain way. Right. That is one way of defining a tensor. Or we can also think about tensor as a machine, right, which produce number when fed with vectors and covariant vectors. If you put a bunch of vectors and covariant vectors into this machine, it will produce a number. And this machine can be considered as a tensor as well, right? And there are notations that we will use. Tensors are classified according to their rank and order. So that's how you know that a vector, you have a value and a direction, right? Like that. For the tensors, we will classify these tensors according to their rank and order. And let's see some examples to understand what this rank and order means. Now, if you the tensors are also classified by the type, and type is normally given inside brackets as n comma m, and m is the number of upper indices and n is the number of lower indices of a tensor. And you will see that from an example. Now, if you consider a scale, scalar, you don't have any indices, right? You just have a number, and that is actually a rank 0 tensor. And the type we write as type 1, 0. And if you consider the contravariant vector v beta, you have one index right here as an upper index, which means it should be a rank 1 tensor, and type should be 1, 0. right? And I think there is a mistake right here in the first one. So I will make these corrections before upload the newer version. A scalar has no indices, right? As I told you, it has no indices. It should be ranked 0 tensor, and at the same time, its type should be 0, 0, right? Here, not 1, 0, right? This is wrong. It should be 0, 0. It should be actually 0. And then you have a contravariant vector, which you have 1 indices, so that it will become a rank 1 tensor, and the type is type 1, 0, right? And then the covariant vector, you have a lower index. Still, it is a rank 1 because you have only one index there, and it's a type 0, 1. And remember the difference between type 1, 0 and 0, 1, right? Because the first one right here inside the bracket represents the upper index, and the second one represents the lower index. Since the contravariant vector has an upper index, it's a type 1, 0. When you have a lower index, as in this covariant vector, it will be type 0, 1, right? And if you think about a higher rank tensor, let's say you have a tensor called T alpha gamma. This has 2 indices, as you see, alpha and gamma. So because of that, it is the rank 2 tensor, and the type will be type 1, 1, because you have 1 upper index and 1 lower index. And at the same time, just see this is why writing the tensors and get used to it is important. For the T alpha gamma, I have not written it in the same, we call this in the same vertical line, right? So I have write alpha, and I have a place that I kept empty here, and the gamma is written after that, right? So make sure this is how you write the tensors. It is very important. And here is another tensor, T alpha beta, which has 2 indices, which means you have a rank 2 tensor again, and type 2, 0. Now, if you get these last 2 tensors, this one is also a rank 2 tensor, and this one is also a rank 2 tensor, because both of them have 2 indices. But the difference is in the type, right? So this one is type 1, 1, because you have 1 upper and 1 lower indices. But this one is a rank 2 indices, that the type is type 2, 0. So that means you don't have any lower indices, but you have 2 upper indices. Because of that, the type is type 2, 0, right? So that's how you differentiate this tensor and this tensor. Right now, our Riemann curvature tensor, which is actually, normally comes across in, most of the time in general relativity. It's a rank 4 tensor because you have 4 indices, but you have if you look at the type, it is type 1, 3, because you have 1 upper index and 3 lower indices, right? And once again, see that when I write the lower indices, I haven't start I from directly below L, right? So there is a space here, and then after that I have started writing it. Right now you can see that a type 1, 0 tensor, which is a contravariant vector, which is written in the column form, right? Now this is a type 1, 0 tensor, and this is written as a column vector, right? So that's how you write a tensor V alpha. And then here is a type 0, 1 tensor, a covariant vector basically, which has 4 components, which is written as in the row form X beta. And about 2 tensors, if you need, you can multiply, And we call these type of operations as tensor product to form a rank 2 tensor, which is, I can see that there is small typos right here, which I make these corrections, and which is a 4x4 matrix. So let's see how it works. Right, so T alpha beta, this is the final tensor that we have. To get that tensor, what we have done is we have multiplied V alpha by X beta. Once again, this is V alpha, this is X beta, and you just multiply this column vector with the row vector. And then once you do the multiplication, you will get the 4x4 matrix, right? Which is basically this rank 2 tensor, rank 2 type 1 tensor, because you multiply a covariant vector with the contravariant vector, right? So these are the components. And if you need to get one component, you normally write T30, so which means V3x0. So that is which component? This component right here, right? So that's how you identify the components. Basically, when you write a tensor, just keep that in mind. T alpha beta, the second rank tensor, means all these components right here, right? Now, in the similar way, you can multiply two covariant or contravariant vectors to obtain rank 2 tensor, right? The only thing is you will still have a rank 2 tensor, but the type will be different. Since you have a covariant and contravariant one, the type is 1, 1 here. But if you multiply two covariant vectors, maybe types, you will have type 0, 2 here. Or contravariant, for the contravariant vectors, maybe type 2, 0, like that, right? The rank will be the same, the type will be different. Now you can see that even a rank 2 tensor, how many components that you have there, right? So that means when you go for these higher rank tensors, they are harder to visualize and can be thought of as stack of matrices. Then even you cannot even think about they as matrices. So they are like stack of matrices. So that's what happens for these higher rank tensors, right? So this is why it's a bit harder sometimes to mathematically understand this theory of general relativity, right? As tensors can be expressed as rows, columns, and matrices, they can be defined as multidimensional array of covariant and contravariant indices. And here is again a rank 2 Minkowski metric tensor, right? So this is called a metric tensor, and all of you know about this tensor. Right. Now, so let me probably stop right here. And the second one is the tensor transformation. From the next lecture, I will start talking about how to transform between tensors, right? Now, for the time being, so make sure that you go through this, especially this section about the tensors, and try to understand. And the second one that we have, right, and also make sure that you complete this question. This question will allow you to understand these concepts about the coordinate transformations that we talked up to now. And they are purely mathematical, right? But you need to understand those. And after that, so make sure that you get the idea how these two different types, covariant and contravariant transformations works. And then just go to the note about the tensors, which explains you how these tensor transformation works, right? I mean, especially I try to understand what is a tensor and what this rank and the type of a tensor means, because these things, having these things in your mind will make it easy for you to understand rest of the lectures, right? Anybody have any questions up here? right? So make sure that, once again, make sure that you go through the note and try to understand it as much as possible, right? Because this section has a lot of mathematics that go into it, and it will be look like this until we, prove or discuss about the Einstein's field equation. It will take few days because I have developed all this mathematics before that to make you understand the Einstein's field equation, right? After that, we will talk about applications. But until that, you need to. So I'm going to, shorter the lecture, and rest of the time I will give you to understand what these things means, right? Basically, it has to be done by yourself, right? So because of that, make sure that you try that problem and try to answer it. So no questions from anyone? Right, so let me stop for today's lecture, and we may meet on Wednesday or Friday, right? Since I have covered the things that I need, we may not need like 3 days for this week. So I will let you know. So there will be one lecture in one of those days, probably Wednesday or Friday, and I will let you know about it. Right, thank you.